Hello, everybody, and welcome to our continuation of discussing sets. We have done quite a bit yesterday, and we just want to maybe remember sets here. So, every time union of two sets, let's say E, U, F. If I visualize that by way of a Venn diagram with my sets in general position, like so, because I don't know anything about them. The rectangle contains the universal set. Everything is in the rectangle. Then the union of the two is just throwing everything together. Let's make it blue. Everything that E contributes, everything that F contributes, pooled together. So everything that is in E or in F or in both. And that's why often we're associating the union with the word or. All right, but there is another way to combine two sets. Ways we need to focus on. The other one is the intersection. Now, by thinking of the word intersection, you might already guess what that is, but let's write it out anyway. The intersection of, let's say, a set E. Now I'm going to use the word and another set F is the potentially new set, and we're going to name it E, and we're going to flip the cup symbol and call it our intersection symbol. And that new set contains only elements that are in both E and F, which is why you'll see we're going to associate the and word with that. Now, to be fair, for union, we could sort of see the symbol as a U. It isn't a U, but it looks very close, I'll admit. I guess the I was taken, so the next letter in the lineup is an N. So you could sort of think of that as an N to help you remember what the symbol looks like. But of course, it's not an N. There's an N. There's the intersection symbol, night and day, right? Though, if you write a little n, I will look the other way. Now, we don't have our examples anymore, right? Let's just write them again. I did not. And I'm probably going to pick ones that are different. I think we had little a, b, and c in what is arguably the best curly bracket ever. Then we have a and b, I think. Maybe a c, d, and an e. And then d was a set that was not related to these other ones. If we have these, then let's take some examples of intersections. We could say, first of all, A intersection C, and we often say just A and C, but we have to know what we mean by that and. It's the overlap. It has to be in both, and we see little c is the only thing that's the only element that is in both. So you can exchange this word for overlap if you want to think of what this is. but officially it's called intersection. If we look at A intersection D, it's what they have in common. They don't have anything in common. There's nothing in the empty set. A intersection B, what they have in common are the elements a and little b. This leads me to some observations. That, first of all, let's sort of go to two extremes and then in the middle. Without specifying any specific set, you could look at these examples, but I'm not too attached to them. First thing here, for any set E, the intersection of that set with the universal set, well, it's the overlap, right? But the universal set contains everything. So the overlap will be all of set E because it's necessarily in the universal set as well. Let's go to the other extreme. For any set E, the intersection with the empty set, well, I'm looking for the overlap between whatever E has and nothing. They overlap in nothing. And then something in the middle, perhaps. Let's say here, if I have two sets, if E is a subset of F, then the intersection will look like, well, being a subset, hopefully you've reviewed from yesterday, very important that we can build on top of that. Being a subset means you are essentially contained in the right-hand set, which means E features in both, no more, no less. So the overlap will be the smaller. And remember, compare that with the union, which was throwing them together, but in that case, the smaller one doesn't contribute anything new that the bigger one doesn't already have, and the union sort of went the opposite way. So yes, these aren't opposites of each other in the technical sense, but they do sort of stand on opposite ends of how to combine sets. Let's visualize this one with our Venn diagram. Get our rectangle going. And I don't know specifically any two sets, so I want to put them in general position. So let's call them E. Let's this one F. And I'm interested in representing or visualizing the intersection. Let's not go the same color. Let's go pink. E intersection F. Well, it's certainly not the outside because those elements don't have anything to do with the sets. Elements in here, they're only an E. They're not an F. I'm looking for those that are in both. These guys, only an F, not an E. But these guys in the middle, they are the only ones that are in both E and F. And of course, then compare that with our union visualization up here, where the union doesn't discriminate. It says, everyone's welcome. Come join the party. Throw them all together. Mix them up. Doesn't matter where you come from, as long as you're somewhere in these sets. Intersection says, no, this is a fancy party. Not just anyone can come. You need to satisfy all of these requirements. Whatever E, if you belong to the E requirement, we can think of these as requirements. Belonging to the set satisfies a requirement, whatever that may be. And if you belong to the set F, you satisfy its requirement. You need to do both, or you cannot join the party. Not very nice, but it's their party. They can do whatever they want, I suppose. All right, so it's very important to understand what each one is saying, what each one is requiring, and the fact that they are very rarely the same. And I think of them as not the same ever, though I guess I could have uh, the rare case that they are the same. When are they going to be the same? Well, see an example. I guess I can make another observation here. And notice that if I take a set with itself, union, I combine the set with itself. What does union do? Throws everything together, but the set is combined with itself. I can't double up elements, so it's just a set. If I take the intersection, the overlap between the set and itself, it overlaps in itself. So yes, there are special cases where the union and intersection result in the same set, but these aren't common, right? Why would I take the set with itself? I already have the set. So that almost never happens. So it's perfectly safe for me to think of these as producing very different things. Righty, let us see what is on the. So in the book, there's some explanation, some examples like we've done, union, intersection, Venn diagram, all familiar things, but sometimes it's nice to see them in written form. Let's look at exercise 5.2. 5.2. 5.2. Where I'm just going to read this first, and we have to understand what it means, what it's asking us to do. Let A, B, and C be any sets. So I didn't use E and F. They're not attached to the examples. Just any old sets, A, B, and C. I want to use a Venn diagram to verify the following equation. A union, no, it's not union, clearly intersection. A intersection of first B union C is equal to A intersection B, then A intersection C, and then the union of those two. So this is sort of an instruction, if you will. Take three sets. If I combine them in the way the left side of the equation says, and if I combine them in the way the right side of the equation says, equal means the same. So the result has to be the same. How do we approach something like this? Okay, so I'm just going to move side smaller. Okay. So let's just write down here. Let's say we want to test whether this is true. We want to examine A intersection B union C versus, what was the other one? A intersection B, remember brackets come first, and then union A intersection C. We want to compare these two. So we're going to do this one and see what the result is first. Then we're going to do that one and see what the result is without knowing exactly what the sets look like, right? So I have to start in my general position. So number one, make it nice and big. Rectangle contains everything. My general position for three sets without knowing anything about them. Well, I now have to start with a layout that covers every possibility. So let's start with A. Let's suppose that's A. Now I know what the general position of two sets look like, so I can put a B down over here. covers every possibility. There's an outside, there's an overlap, there's something with just in one set, something just in the other set. But when I now want to position another set C, I need to cover all possible all potential overlaps that could occur. It has to be positioned over here. C. There has to be something on the outside still. There has to be something that just C has. There has to be an overlap between A and C, but not B. C and B, but not A. And then an overlap of all three, covering every possibility that could happen. So that's my general position, always. Even if I know something about the sets, I can still do that. And if one of these regions turn out to be 0, I'll just put a 0 there. There's really no downside to starting in the general position. I need to understand this general position. Now I'm going to maybe write it over here. A intersection B union C. I need to combine them like this. However, this isn't a one-step process. This can be broken up into a couple of steps. How can we make this a little bit better? So let's use some colors. Colors always work. Always helps. Let's go with pink. I'm gonna make this pink. I know it's not my ultimate answer, but that is what I'm going to start with. Then later on we'll combine it with A, see the result, and this is what the side instructions give me. Then I have to do all of it again and combine it in the way the right side instructions tell me to, and see if the result is the same. We have to understand the plan of attack here. It's not a short thing. It's a big thing, but it's an important thing. And in the meantime, I'm practicing Venn diagrams as well, and emphasizing the intersection union and sort of instruction for combining sets. A lot of things are practiced here, so it's a very, very handy exercise to do. So I want to take my time and really understand how we approach this. Stepwise, slowly. Just number 1 first, see the result. Then just number 2, see the result. And hopefully, if the equation is true, those results match. But within this number 1, the brackets tell me do this first, right? BEDMAS, brackets come first. I'm going to use colors. I'm going to use pink. Well, I know what the union does. So right now it's just B union C. Throw B and C together. Now people have a really hard time sometimes. When I do this pink, there is no A. A doesn't exist. There's no A for the next immediate step. There's B combined with the union with C. I don't see an A. What A? What are you talking about? There's no A. Throw B and C together. Sorry, I shouldn't have used the and there. Throw B with C together. Now, the instructions also say, once you have the pink area, combine it with A in this way. So let's make A blue. B. Not much to do. I just have A, so I don't have to modify it in any way, but I could certainly color it blue. I don't want to be too thick with my lines here so that I can see what's behind it, but hopefully you can still see. Now, they say, combine the blue and the pink with an intersection. Intersection. Actually, I'm not going to do it like that. I'm going to do it like this. Find the, actually, no, this way. Find the blue, the pink, an intersection, and that's going to give me, it's close. That was that's going to give me, you guessed it, purple. But it says intersection. Intersection is overlap. So it has to be in both. It has to be blue and it has to be pink. Which areas are blue and pink? It's these guys. Now I'm just going to outline it so it doesn't get too confusing visually. Like that, right? Just outline it. Blue and pink, blue and pink, blue and pink. No, 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 no. No, certainly not the outside. So I get this sort of double flower petal thing as the result if I did what number one, the left side of the equation, says. Now I'm going to do the exact same thing, but according to number two's instructions. So now it's a fresh start. Number two said A, what? Intersection B, then A intersection C, and then union those two. Well, let's just set this up again. Big general position for 3 sets. Like so. Let's call that one A, that one B, and that one C. And of course, the rectangle, as a reminder, contains everything. So now, I'm going to recycle my pink and blue, because why not? I guess the first one, it doesn't matter. Pink. Let's make, brackets come first. So let's make this first bracket pink and see what that is first. Well, that doesn't concern C. This bracket says combine A and B with an intersection. A intersection B is the overlap between A and B. There is no C there. What's C? I see no C. A overlap with B. It's very hard for some people to not see everything at all times. No, there's A with B. There's no C there. Next bracket is A and C. There's no B. That immediate purpose of finding that bracket that we will color blue. A overlap with C. A overlap with C is now remember, this is a brand new Venn diagram, brand new instructions. I have to forget what I did in number one. That doesn't exist for a little bit. I have to selectively look, and that's really hard for some. It's like, oh, it's obviously the overlap of pink and blue, right? No, that was a number one instruction. We've passed that. It's gone. Move it. Move it away from your sight. Doesn't exist right now. This instruction tells me to combine pink and blue with a union. Union. And that's going to give me its own purple. Maybe I should have used brand new colors. I didn't. Too bad. Own purple. So now what does the union require? It's a good test. Union requires throw everything together. As long as you have a color, come to the party. I don't discriminate which color you have. I don't care if you have both. You could, maybe. I don't care. Just have a color. Get the same result. Because I want to, because it said combine it with a union. Happens to be the same. See here? Same result. And therefore, why am I still purple? I don't know. Therefore, it's equal. A intersection B C is equal A intersection B A intersection C. Now, there are many of these identities in terms of how the union and intersection are related to each other. I'm hesitant to refer to this, but I will, and hopefully you just listen. Uh, Compare this with 2 times 3 plus 4. How do I simplify this? I multiply it into the bracket. 2 times 3 plus 2 times 4. Now, I'm not saying union is plus and intersection is and. These are generalizations, past numbers, bigger objects, objects containing objects. They're not numbers anymore. It's much more complicated. But you can see the parallel between these two properties. The set property is just sort of a more general version of this distribution property. So don't think, oh, this is arithmetic. It's sort of arithmetic for sets in a way, but that arithmetic is a little bit more complicated. It's not. You can't say, oh, well, this works for numbers, so it works for sets. No, 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 no. It's not a direct correspondence like that. So just be careful. But we do notice similarities, and that certainly helps me to understand what we're trying to do here. It's just more complicated in this set um, environment by that, but it's interesting to see that there are some similarities. Venn diagrams are just wonderful to visualize. We're visual people, most of us. It's hard to think of abstract things, but when I can visualize circles and colors and overlaps, it's nice. I like it. Okay, so let me refer to a problem now before we head into this next bit. You'll see that problem 5.1 is very similar. Same wording. Use a Venn diagram. It specifically says use a Venn diagram. There are other ways to do this, more algebraic ways. That's not what it's asking. It's asking you to draw the Venn diagram. Use color. Do what you can to help yourself to verify something is true or not, some equation, right? You see here, this one, this number 1, it looks very similar. It's not the same. It's not the same. The other one, the signs are flipped. The the union intersection signs are flipped. But we do this in the exact same way. And then you see there are others here, 2 others, with this C thingy. What's that? We haven't done that yet. So wrap this up with one more way to make, it's not really make a new set, but I guess kind of is. Not making in terms of uh, combining like the previous 2 were, but there is one more thing to mention. Really not hard on its own. If I can see my colors, please. And that is the complement. Complement of a set. Let's write it out. The complement of a set, let's call it E, is named E with a little c. It's a different set, a new set, if you will. But it's coming just from one. It doesn't come from combining 2 sets or multiple. Given a set E, this new set is called E complement, is the new set that contains all elements not in E. Let's visualize that. Now, it's only coming from one single set, so I only need a single circle. There we go. In my universal set rectangle of everything, there. Some of the elements are in E. Some maybe not. The complement, let's make it right so I can see it. Complement is everything else. Everything else. Visualizing it shouldn't be too bad. It's everything that's not in E. So for example, if I look at my uh, examples from the very start, A, B, C, D, example, if I do, let's say, remember, set A was little a, little b, little c, then A complement is literally everything else in the context of what the elements are, in this case lowercase letters of the alphabet. So everything else would be D, E, F, and so on, all the way to the end. Literally everything else. So an observation that I can make here, first of all, so important. If I take E, any set, and I take the union with its complement, then what does the union require? To throw everything together. And if I throw the circle with the outside together, I get everything. If I look for the intersection, that now looks for overlap. What is common to both? Well, by definition, the complement is what the set is not. It's the outside, the rest. There will never be an overlap. Empty. Let's take a couple more. If I take any set E with the universal set, any set E intersection. No. Sorry. I don't think that's necessary here. We just need the complement now that I think about it. Yeah, this is enough. This is enough. We don't want to make things unnecessarily complicated. We already have all the others covered. We did union and intersection. So never mind that. So the set, any set, together, thrown together with its complement makes everything. And there is no overlap between the two. So now, let's see. I think I want you to just definitely do number one in problem 5.1 first. Be perfectly happy with your strategy, how you're using colors, what to look at when, how to work systematically, all of those things. Number 2 and 3 are the same, but it involves this complement, so my strategy is the same. I just have to systematically go about making these results. Brackets come first. So for example, in the first one, I would find the union of A with B, make it a color, and then the complement is everything that does not have that color. See the result, and then combine it in this way and so on. But we have Q&A sessions, but to discuss these further. But I want you to really put some effort in first, because everything sort of comes together here. Venn diagrams, unions, intersections, complement, everything comes together so nicely for very, very good practice. Okay. Another kind of question that really tests if I understand union, intersection, not so much union, because union is often very vague. Oh, if you have the first property, if you have the second property, yeah, you're all welcome. It's a little hard to really get on top of it right now. That'll be the next chapter, session, well, section. But we can still put a more practical spin on this. Now, let's read this together first, and then discuss it in our remaining few minutes. From a box of 15 distinguishable textbooks. They're all different, they have different titles. I can tell them apart. There are 5 engineering books, 6 psychology books, 4 economics books. Sarah closes her eyes and randomly arranges 4 books on a shelf. Let E denote the set that all books on the shelf are psychology books. F, the set that no engineering book is selected. G, the set that at least one book from each subject is selected. So this is why I like to think, when it comes to something more practical, I like to think of sets as restrictions or requirements that I can, being Sarah, I can select any 4 books and arrange them on the shelf any way I want. But I can also place extra restrictions on what that arrangement of 4 books should look like. For example, E has the restriction that they should all be psychology books. Now I can't just do anything. Some of these arrangements will satisfy the requirement that E has, and some of them won't. Some of them will be in the E circle, some of them won't. Now I'm not doing Venn diagrams here. I'm just thinking about what this set is really telling me or requiring. So I'm doing something practical, some experiment with a result. The result is I look at 4 books on the shelf. And then there are restrictions limiting the possibilities of that experiment. And I have a restriction E, I have a restriction F, I have a restriction G. So initially, sort of in the mathematical sense, sets are a little more abstract. But once I sort of switch over to a practical action being conducted, these sets just become restrictions. And combining those restrictions produce new restrictions. And it might be helpful to think like that instead of too abstract. Because practical people can imagine doing something, it's going to make it easier to visualize, just in a different way. It doesn't have to be that abstract. And in doing that, we're sort of heading towards the statistics subject. Now I'm going to do problem 5.2 because in the past when I leave both problems up to you, it is a disaster. But there's a big problem 5.3, so you still have a lot of stuff you can practice if you want to. Okay, so now the first question here is describe the set E complement, F complement, G complement in your own word, and the intersections as well. So now whoa, what happened there? I am going to see this just on my other screen. I have to. So if you're watching this maybe after the fact, pause, get your book, and really make sure of what these sets are. There's a lot of words there. Read it over and over and over, and you might have to watch this again later. There's a lot of words, and you really have to know what each set is requiring. Okay, so I'll just do it systematically. I'll say it very short in a short way here. E is all psychology, requires all psychology books, right? Then I want to say in words, not a little bit longer than this, but because this is in the book, the requirement for E, I'm just reminding myself. I want to write a few more words when it's not already done. E complement is a requirement. It's the opposite requirement. Now, many people might be tempted to say, oh, well, if E is the requirement that my arrangement should have all psychology books, then E complement is the requirement that it should have no psychology books. But remember what we said here, that E with its complement thrown together needs to make everything possible. Universal set, sometimes called the sample space. everything that's possible when I merge these two. So if I say E complement is the requirement that there are no psychology books, then what about the arrangement? Maybe psychology book 1, maybe engineering book 1, maybe economics 3, and maybe psychology 4. This is a possible result that I could get. It's in the universal set of all arrangements possible. Therefore, it has to be somewhere among the set and its complement, because together they make everything. Well, certainly it's not in E. It's not in E, because it's not all psychology books. E is very restrictive. Therefore, I have to rephrase the complement so that it covers these ones. I can't say no psychology books. Then this one's not an E complement either. It has to be somewhere. So I have to phrase it a little bit more general. All arrangements of 4 books, of course, with 0, 1, 2, or 3 psychology books. Or you could say not all psychology books, but I don't like that because it's a little bit of a cheat. That's not always going to work. Okay. And if you recall, this is the negation. We've seen this before in 142, though it's not necessary that you remember that. Next up, they tell me what F is. F is the set, the requirement, no engineering books. No engineering. So for example, something that could be in here, no engineering books, psychology 1, psychology 4, economics 1, economics 2. As long as there's no engineering, it satisfies F's requirement. So now what is the complement of F? Understanding that together they have to make everything. It's not all engineering books, because then, like this top example, it's not in either one. I can't jump to the other extreme, because together they have to cover everything. Said here. So if F has the requirement that I can't select any engineering book, F complement has all arrangements with 1, 2, 3, or 4 engineering books. So it's important here that I should have led with that, I'm sorry, that we understand this is my Venn diagram in this case, containing everything. What is an element? Element is a single arrangement of 4 books, not a book. An element is the result of the action being done, and in this case, Sarah arranges 4 books on the shelf. And then she's done. That is one result. That's one little dot in my Venn diagram. Some dots will be inside circles, some dots will be outside circles, depending on the circles. But it's not a book, because she's not done performing her action, completing her experiment. One thing now is a single sequence consisting of other little things. G. I might not do the whole thing, but at least it'll get you started. What is G? G is the set that at least, or the requirement, that at least one book from every subject. Each subject should be represented. For example, something that is in G, well, the top one. 1, psychology 1, engineering 1, economics 3, psychology 4. Of course, I have more books than subjects to select, so some subjects will double up. That's okay. But when I look at the arrangement, remember this is a single thing in the G circle. It's a single dot in the G circle. Then I see every subject. So G complement needs to be everything that G is not requiring. G is requiring something very specific. Every subject needs to be visible in my arrangement. So G is simply uh, the set of all arrangements with, say it like this, at least one subject missing. Could be all psychology books. Then engineering and economics are missing. Doesn't have to be. I could just miss one. Something has to be missing. Otherwise, if nothing's missing, it's in G. Together, they have to make everything. So it's really just a spin on that negation question, if you remember the start of 142. And it takes some getting used to. It's very important to start right, to understand what is being created. That's what we call an element. That thing that's being created could be big. It's a single thing. And if the experiment plays out in a different way, of course, that thing is going to look different. Then the sets give requirements on what these elements can look like to be included in that set. We have 3 minutes left. Let's do E intersection F. What is that requirement? Well, now I have to remember the individual ones, right? E is the requirement that the arrangement has all psychology books. F is the requirement that there's no engineering book. But by being all psychology books, I am automatically satisfying the fact that there are no engineering books. There are other ways to not get engineering books, maybe a mix of psychology and economics. That is an F, but that's not in E, because E requires all psychology books. And I'm looking for the overlap. I'm looking for the arrangements that are in both. So E requires all psychology books. F requires, yes, they could be all psychology books. Then I'm happy. But I also have some other stuff. So it's a little bit more difficult to visualize these. I have to talk through for myself what each one's requirements are to sort of see how they're related. In this case, since E's requirement is already in F, but F has more. F can be satisfied in this way over here. And E doesn't like that. But anything that E has, which is arrangements with all psychology books, F will be happy with that as well. So any element in E is necessarily in F as well. And I know that the if I take the intersection of two sets, one being a subset of the other, then the intersection is just the smaller one. Meaning that this is the same arrangements requirement that the arrangements have all psychology books. So we're putting a little bit more of a practical layer on top and really testing. I understand what elements are and how they fit in to different sets just being requirements. Can I then interpret the complement, intersection, not so much union. It's a little bit, get to that later. Can I sort of mix and put that abstract understanding on top of a practical situation? Because ultimately, if it's just an academic exercise with abstract concepts, it could be fun sometimes, but it doesn't help me that much. But if I sort of merge the abstract and the practical, then I'm really getting somewhere in my thinking and my development. So there is a lot to do. This these two problems, we're not done with 5.2, right? I just wanted to get you started because in the past, if I leave people to just do this on their own from the beginning, it doesn't end well or it doesn't start well. So now you have at least an idea of how to think about this. Finish 5.2. Uh, there's a whole new 5.3 with many, many questions. I'll just emphasize here in 5.3 number 2, they talk about sample space. That is just the universal set. Universal set. When you put a practical layer on top, then you're heading to statistics, and for some reason they love to change all the words. They don't talk about elements, they talk about outcomes, they don't talk about sets, they talk about events, they don't talk about universal set, they talk about sample space, but all those things are the same. We don't care. Lot of wonderfulness. Is that a word, wonderfulness? No. Wonderfulness in problem 5.2 and 5.3. Do the Venn diagram ones first. There's more we have to do still, of course. Don't go past 5.3. But there's a lot of stuff here. A lot. All good things. All good things. It doesn't have to go well from the start. It's going to be a struggle. Just make your peace with that. This is going to be confusing. If you've done 142, remember the first time you worked with negation and those things, there was a little bit of a struggle. But by the end, you look back, oh, it was not that bad. All these things just take time. It takes time. It takes time to discuss and talk about it. You'll find that once we talk about these things, it gets much better. But that discussion is only effective if you have started, seen how far you can get, thought about it on your own, so that we can identify where you got stuck and be more efficient. Doesn't matter how fast or slow. I don't have my schedule open. Let's look at the schedule. See the schedule. Let's see here. Zoom in a little bit. Where are we now? We are on Thursday, I believe. Now, we are continuing this. I don't know. I'm going back and forth, to be honest. Let me just change this. I'm going back and forth. Should we have our Q&A tomorrow, or do you need and swap these two? Or do you need the weekend and the Q&A would make more sense on Monday? Though we do have a Sunday morning. Because we need to think about these things first, and maybe some people need the weekend. So I'll leave it like that. Even though we'll go ahead to the next little topic, they're not, they are related, but not that much. Maybe people need the weekend to just figure out where they get stuck. Is there even a problem? Really put some time in. And then not tomorrow, Sunday, Monday, Tuesday, we'll have some time to discuss things. It's important to have that dialogue, not feel isolated and get all negative, but understand these things are going to take time. If I'm going to learn to play piano, if I go sit in front of a piano, those first lessons are going to be frustrating and it's going to seem impossible. I will never play this. How do people play this? I watch YouTube videos. They're amazing. How do they do it? No one can explain to me because it's just time. Time and things just clear themselves up slowly. But we need that discussion to help sometimes. Time, patience. And that's hard. You'll see in elementary school. Whew. Patience is something kids do not have. If they don't know the answer right away, they conclude, oh, they're just stupid or their brain doesn't work that way or some other lame excuse. No, it's just patience and time. It comes with experience, I suppose. All right, think about it. Do what you can. If you can only get to it on the weekend, that's good. We have a weekend. Good. But don't waste the time. It's going to be beneficial for you on many different levels. All right. Any last words? All right, then we will continue this tomorrow with a related topic. Yeah, it's kind of related, but not exactly the same. All right, until